2,000 aluminum cans roll off the line every minute. One can every 0.03 seconds. Here's how a single body maker stretches metal 400% without tearing. If punch temperature rises by just 10 degrees Celsius, wall thickness drifts and thousands of cans fail. Let's step into the line. Aluminum cans are the most mass-produced beverage container on Earth. A single plant makes over 2 million per day, each formed in under 2 seconds from a single disc of metal. But precision is everything. One misalignment or thermal drift, and the line collapses. Today, blanking, ironing, trimming, necking, coating, printing, and inspection. And one hidden control loop makes 2,000 cans per minute even possible. Every can begins as a 0.28 millimeter aluminum sheet. A punch presses out round blanks at 400 strokes per minute. Each blank becomes a shallow cup, the first shape of the can. If lubrication film is too thin, aluminum galls on the die. Too thick, the blank slips and folds. The cup looks simple, but uniform thickness here prevents downstream failure, because everything that follows stretches this metal to its limit. The cup enters the body maker, the heart of the line. A hardened punch drives it through 3 ironing rings, thinning the walls from 0.28 to around 0.10 millimeters. The aluminum stretches over 400%, but must remain perfectly smooth. If punch temperature rises by 10 degrees Celsius, the metal softens and dimensions drift. If friction spikes, the can tears instantly. This 2-second sequence sets 80% of the final geometry. But even after forming, the top is unusable. The can is still too wide for a standard lid. The top edge is trimmed clean to prepare for necking. Necking reduces the diameter in small steps, often 10 to 12 dies in sequence. Each die must align within tenths of a millimeter. If necking force rises by more than 5%, circumferential wrinkles form instantly, collapsing the can before the next die ever hits. Too little force and the step isn't clean, too much, and the wall buckles. The final neck shape determines which lid fits and whether the can survives carbonation pressure. Freshly formed cans are washed, rinsed, and coated to prevent corrosion and protect flavor. An ultra-thin polymer layer is sprayed inside and out. But even perfect coating fails downstream if curing drifts outside its 200 degrees Celsius window. The polymer stays soft, and the print tears at line speed. Curing locks the coating into a hard, food-safe surface. Only then is the can ready for its identity, full-speed printing. Cans pass through high-speed decorators that apply up to 6 colors. Registration holds within fractions of a millimeter at 2,000 cans per minute. Ink viscosity must stay between 25 and 32 seconds in a Zahn cup. Drift outside that range causes color bleed and ruins registration at speed. Roller pressure stays within plus or minus 0.1 bar to avoid over-squeeze and haloing. A final varnish coats the artwork, then passes through a curing oven to harden the finish. Every can is washed, dried, and measured. Vision systems scan for dents, cracks, or neck defects. Dome pressure tests inflate the base to verify structural strength. Any deviation in wall thickness or coating adhesion triggers rejection. Only perfect cans continue to filling plants, where they'll withstand carbonation, stacking, and transport. 2 invisible feedback loops keep the entire line stable. Sensors track punch load at 2 kHz, correcting lubrication flow 20 times per second. Necking dies use servo feedback that adjusts axial pressure within 50 milliseconds to prevent buckling. Bearing temperatures are sampled every second. A 12 degrees Celsius rise signals imminent drift in wall thickness. Dryers monitor exhaust at 10 readings per second to maintain the curing window. Line controllers synchronize all stations in a plus or minus 3 millisecond window. Miss it, and the entire train collapses into jammed cans. This is the hidden system that lets aluminum stretch 400% without tearing, at thousands of units per minute. From a flat sheet to a finished container in under a minute, every can you've ever opened passed through this precision sequence. High-speed forming, thermal windows, pressure control, and millisecond timing turn thin aluminum into a structure that holds carbonation and survives global distribution. Tell me which high-speed forming line we should break down next, and I'll show you the hidden control system that makes it possible.